recording. Okay, so properties of real numbers, key terms. Opposite, the opposite of any number. A is negative A. If it's negative, the negative makes it positive. The additive inverse is same as above. The additive inverse and the opposite of a number are the same thing. Okay? Two ways of saying the same thing. Additive inverse, opposite, they are the same thing. Okay? The reciprocal of any number, A, is 1 over A, whether it's positive or negative. If it's already a fraction, for example, 2/3, then the reciprocal of that is 3/2. Okay, that's what the reciprocal is. You just take it and flip it over. Make it a fraction, flip it over. Reciprocals have the same sign. Okay, and the multiplicative inverse, same as above. The multiplicative inverse is the reciprocal. The reciprocal is the multiplicative inverse. They're the same thing. Two ways to say the same thing. Okay. And yes, my handwriting is crap. You'll get used to it. If you can't read anything that I really write out, all you got to do is ask. I will explain. Okay? And after you've been in my class for a while, you get to kind of pick up on it a little bit. Okay. Questions on this? Hey. Next page. There we go. Okay. Oh, I forgot to put the commutative property of multiplication on there. I have the one for addition. I do not have the commutative property for multiplication, which is A times B equals B times A. Commutative. When you commute to work, you move. So the commutative properties are properties of movement. You're moving the objects. Does that make sense? This is probably the hardest one for students to remember, is which name goes with which. You will have on your quizzes and on your chapter test, you will have to identify the property. And you will have to use the correct name. There's only a couple of them, the commutative and the associative and the distributive. Okay, those are the ones in particular you really have to have down the names. The commutative property is about moving. Notice that the commutative property is true for addition and multiplication. The commutative property does not work for subtraction. 3 minus 2 does not equal 2 minus 3. Addition's commutative, subtraction is not. Same thing for division. 2 divided by 3 is not equal to 3 divided by 2. It works for multiplication and addition. The associative property, same thing, addition and multiplication. The associative property has to do with grouping. When you associate with somebody, you are grouped with them. An association is a group. In the first one, B is hanging out with C. In the second one, B is hanging out with A. It's just changing who it wants to be associated with. That's what the associative property is. It's how do you group things. If you change the grouping without moving anything, but just how they're grouped, that's the associative. An association is a grouping. The associative property is how you group them. Once again, only works for multiplication, and addition does not work for subtraction or division. Identity property of addition and multiplication. Anything plus 0 is itself. Anything times 1 is itself. The inverse properties, and we already talked about the inverses, right? The inverse of A is negative A. It's called an inverse because when you add them together, you get 0. Anytime you add two numbers and you get 0, those two numbers are inverses of addition. If you multiply two things and you get 1, those are multiplicative inverses. Okay? So A times 1 over A is 1. That's where the inverse properties come in. Okay? And then the last one, the distributive property. You can distribute across addition. You can distribute across subtraction. Think about the distributive properties handing out papers. So I just toss them in a big pile and say, go for it? No. I distribute them across the front of the rows, and then you guys distribute them back. It's spreading out. That's what distribution is. Okay? Questions on that? Does anybody need more time? Okay. Throughout history, numbers have progressed based upon need. One of the things I study, one of the things I enjoy, is mathematical history. I like to read books about the history of mathematics, about mathematicians, and so on and so forth. I'm a math nut, that's what I do. One of the many things I do. Numbers have progressed based upon need. The natural numbers are also known as the counting numbers. 1, 2, 3, 4. You count things off. Those are the counting numbers. They're the natural numbers. They're the ones that you first had to do. How many chickens do I have? You have to be able to count the number of chickens you got, right? How many goats do I have? And they're all whole numbers, because if you have a half one, well, they're no good to you. You go ahead and eat it and get rid of it, because you don't eat half of one and save half for later, because when they embed the numbers, it's not like they have refrigeration. Okay? And that's where they came from. Eventually, somebody said, well, how do I see that I don't have any? What's a way that I can't keep it down? So they actually started keeping track of numbers, and writing things down and keeping track of them. They had to come up with the idea of zero. Now, 0 is an important number. 0 is one of the most important numbers in existence. Not for standing for nothing. That's great. It's nice to be able to have a symbol that stands for I don't have any. But 0 is really important as a placekeeper. Otherwise, how do you know the difference between 1 and 100 and 10 and 1,000 if you don't have 0? You don't. And that's why 0 is such a big deal. It's not a symbol for not having anything. It's not a symbol for a zero amount. It's a symbol for keeping place. Otherwise, 11, 101, 110, 1,001, 1,100, 1,100, those are all the same thing without 0. You got 2 ones. You don't know what there is without zeros to go with them. Does that make sense? Okay. Integers. Integers come from when we started having negative numbers. Okay. Notice what's missing from the first 3 ones. Any sort of fraction or decimal. Okay. And then we get to rational numbers. Rational numbers are any number that can be written as a fraction. So something that is a fraction is a rational number. All of these that pre-exist up here are also rational numbers. Because I can take any one of those and make it a fraction by putting a 1 underneath. Okay. Decimals are where we start to have issues. If I can make a decimal into a fraction, it's a rational number. 0.25. Oh, that's 1/4. I can make it a decimal. 0.3 repeated. That's 1/3. That is a rational number. Any decimal that terminates, any decimal that repeats itself in some manner is a rational number, because you can make that into a fraction. Some of them it's harder to do than others, but you can do it. Irrational numbers is any number that cannot be written as a fraction. Okay, there are lots of irrational numbers. The most common of which that you guys think of when you think of irrational numbers is pi. Pi as a number, if you write it out as a decimal, never terminates and never repeats. It's an irrational number. When you do 3.14159, you're using an estimate of pi. Pi written as itself is exact. Anything else is an estimate. Okay. But they're not the only ones. The square root of any non-perfect square is also an irrational number. The square root of 2 is irrational. Square root of 3 is irrational. Square root of 4 is not, because the square root of 4 is 2. But all square roots of non-perfect squares are also irrational numbers. When you take the square root of 2 on your calculator, you get this big long decimal. That's only part of what it is. Because once again, that decimal goes on forever and never repeats. Okay? And then you have real numbers, which are all of the above. Are there numbers that aren't real? Yes, there are. They are imaginary numbers. And we will deal with those in second semester. Okay. Questions? Okay. Now here's what we want to do is we want to fill in this Venn diagram. And I don't really think of it much as a Venn diagram. It is technically, but when you think of Venn diagram, when you think about it, you got a big circle, you got another circle where they overlap, right? And here's all this, here's all the kids with blue eyes, here's all the kids with brown hair, and the one in the overlap are the kids that have both, right? Okay, or blue eyes and green eyes, and then you got the weirdos in the middle that have one of each. Okay, so that's typically what people think about when they think about a Venn diagram. Technically, this is a Venn diagram, and the stuff on the inside is the most restrictive. So using the ones we did before on the previous page, we want to fill this in. Now, what group of numbers was the most restrictive group? What was the group that was the most restrictive? The one that had the least stuff that could be part of that group? The natural numbers. So your most restrictive group goes on the inside. So right here are your natural numbers, because it's the most restrictive group. Does that make sense? What was the least restrictive group? What was the one that included everything? Real numbers. So this big box, it's all the real numbers. Because everything is in there. Does that make sense? So I want you to take a minute, and it shouldn't take you much longer than that. Fill in the rest of those boxes using the numbers that we just talked about. Okay, that should be long enough. So if you think about it, it really kind of makes sense. The natural numbers, a group that's a little bit larger than the natural numbers, would be the whole numbers, because it includes all the natural numbers and 0. Okay, and then the one that's a little bit larger than that, it includes all the whole numbers, would be your integers, because it's all the whole numbers plus the negative whole number, so to speak. And then the next one for there is rational, because every one of these are rational numbers, because I can write every one of the ones inside there as a rational number. This little box over here all by itself are all the irrational numbers. Which kind of makes sense. You can't be rational and irrational at the same time. Think of your friends. And the imaginary ones. Imaginary ones are over here. And we use I for the imaginary numbers, which we will do next time. Actually, I is the imaginary number. Okay, we will do those in second semester. We will deal with I in second semester. But imaginary, once again, you can't be real and imaginary at the same time. Okay, these are not Schrodinger numbers. And if you don't know who Schrodinger is, shame on you. Okay. Questions? Because I do believe that's it.